Welcome to the Contractors Institute. My name's Richard Elsey, and I'll be hosting this module for you. We're going to look at some issues with blueprints. Okay, blueprints and problem solving, I guess. All right, so here's the plan set. Now it's the Chaskill Park, okay, museum and concession stand. Now we're getting ready to look over this. Now, notice how it's set up. It gives you the title, and there's our logos. Ooh, ah, but, that's who we are. So if you need any continuing education or exam prep, upgrading a license or getting another license, or you want to look into a code official, building inspector, plans examiners, and so on, do private inspections yourself. Okay, so either way, we're here for you. Your paperwork, if you needed help with it. We have a business service that processes all that. So, give us a call. So look at the index of drawings and figures. First thing we want to look at here. Now, notice how it's labeled Civil and Underground Drawings, C1 to C5. If you look at the way the pages are numbered, it will always tell you where you're at in the plan set. In other words, if you look and the page number starts with an A, well, you're in your architectural series of prints. If it starts with a P, well, those are your plumbing. Swimming pool, SP. So you can always tell by the plan set you're in by simply the way the pages are numbered. Okay, and that's something important to look at. Now, typically we don't get a whole set of prints. We only get the portion that we need. But we went ahead and put them all together so you could see how they all work together. Well, the initial considerations. Who will provide the property? Is it the owner or the contractor? Now, not only is it important for us to know, but for lien laws, okay, we need to understand that. Who will provide the design services, the contractor or design professional? Okay, that's pretty important to understand. Who is what is the contracting method? Direct relationship, construction management, design build, phase or fast track or turnkey. Okay, again, that's up to each individual. And what is the contract type? Are you looking at a fixed price, or nowadays with the price fluctuations, cost plus, or unit price? What are the payment terms? Are you're going to draw schedule, some type of progress payments? How did you get that laid out? Okay, which once again, that's first thing we want to understand is how we're getting paid. All right, now I just want to look at some contract types. One type we have is a fixed price. That's what we call the lump sum or hard dollar. So here I'm going to give you a price for a swimming pool that I'm not going to be able to build for about a year after permits and materials. Here's how much it's going to cost you. Now it's like, geez, guys, how much can change between now and when that pool actually gets built? Real scary to do right now. Then we have unit price, usually used where quantity of work, okay, will be performed will vary, okay. And then we have the cost plus, usually used where scope of work cannot be specifically be determined in advance. Variables include cost plus a fixed percentage or fixed fee or percentage savings. May contain not to exceed clauses. Okay, so something may not exceed this much. All right, here's just where we're trying to scope out our architectural engineering services, So we really got to stop and slow down, when we do this. We got to have a survey. We got to look at the site, which is notice all that's civil. Before we even get started building, we're in there doing our civil work, our demolition, steel, wool, masonry, that's all under civil. Now the structural, demolition, concrete, steel, wood, masonry, okay, that's all going to be all of our structural areas. And then we have our HVAC, elevators from our mechanical. Our electrical is going to do the electrical. The site work is dirt contractors going to come out and do our soils. Okay. And then we have our architect, looking at our wood, our masonry, our roofing, okay, and telling us what the design is and what material is going to be used. Now, drawing documents and specifications. Now, that's what I want to look at, and that's what the whole course is about, I guess, is looking at plan sets and getting used to looking at them. Guys, there's only one way to get used to them, and that's to sit down with them and start, doing little takeoffs. After someone else has done a takeoff of something, do the same thing. See if you can do it, and come up with the same answer they did. Typically that's the only way that we learn how to really get into plan sets is just use them. Well, that's anything. We have to sit in front of it and play with it and, kick the tires and push the buttons and, make mistakes, and then we figure out how it's actually done. This is no different. It's just a matter of looking at it. Now, keep in mind, okay, binding true agreements. When bidding or negotiating is over, the agreement is executed. This binds the documents together firmly and permanently. Now, we sometimes when we think and we looking at contracts and how we're doing the job, a lot of us, have built under AIE contract documents, American Institute of Architects. Some of us may not like them, but they're black and white contract documents, so everything is there for us. So for some of us, we love them and other people hate them. It's like a split right down the middle, but they're contract documents. That's all they are. Now, once you understand them and how to use them, they're great, but we have an agreement, which, think about it, all the addenda, the drawings, the specifications, conditions of the contract, the bidding requirements, that we have any modifications to the conditions of the contract. Okay, that's, where we're sitting down, getting ready to go. Now, again, this looks familiar to you. You have the agreement, supplementary conditions, general conditions. The important thing, everything has to work together. We all work together. Now, there's a mistake already, I see. CSI now, there's 50, and I'll show you here in that in just a second. I guess when I upgraded the show, I didn't miss that little piece right there. So we have an agreement now. Is the 101 if you're looking at your AIE contract documents. Okay, it's the agreements. Now 201 is general conditions. That's what pertains to the architect and the contractor, and the owner. So that's what, a little bit of everything for us. Now your 401 is your contractor subcontractor agreements. So that's from you to your sub. Okay, your agreements. Okay. Now we have the specifications. Yeah, none of us like to read them, but we have to, and we have to slowly and thoroughly read them, because remember, if it changes in the specifications, it's going to change on the plans. So the purpose of specifications: define information about materials and the exact methods of fabrication. Additionally, they prescribe the quality of the materials and installation. An accurate estimating depends upon exact understanding of these specifications. That's what I said, you got to stop as you're doing your estimates and make sure you read the specifications to make sure it doesn't change anything or add to it. Now, I mentioned CSI Master Format is now 50 divisions. 50. It went from, it was actually 16 technical divisions, but then there was a division 00 for procurement and contract requirements, bidding requirements. Um, so making it 17. Now there's 49 technical divisions, but we also have a division 00. So that's why we have 50 in the master format. Okay, so they open them up quite a bit. So division 00 is procurements and contracting requirements, you know, and then they start breaking them down into the different groups. Okay, we have division 1 is general requirements. And as you can see, I have them up on the screen for you. Division 2, existing conditions. 3 is concrete. 4 is masonry, which are the same. They didn't change. 5 is metals. 6 is woods, plastic, and composites. So, in other words, everything that pertains to wood, plastic, and composites are going to be found in the Division 6. Now, you got to remember, this is a standard construction specifications institute. A lot of accounting programs use the CSI format. Scheduling programs use the CSI format. You know, so this is a standard across the construction industry. You know, we have Division 7, thermal and moisture protection. 8 is our openings. 9 is our finishes. 10, specialties. Okay, 11, equipment. 12, furnishings. Now, I'm just going to take a second and let you read them. Now, notice the ones at the bottom, you know, under conveying equipment 14, they're reserved. That means they don't want to use that section, so they're reserving it for future use. And that happens quite often in the CSI. So whenever they take something out, they don't just put something else in its place. They reserve that spot just in case. Now here's 20 through 29, and I'm going to let you read them real quick. Now remember, at any point during the show that if you need to, you can just reach up and hit the pause button and slow down, and then you can go back and read them all for yourself and see if you missed anything or I went over it too quick. Okay, but I'm just trying to give you a second to read them for yourself so you can see where you fall in. Here's Division 30 to 39. Earthwork, exteriors, utilities, waterways, marine construction is 35. Okay. Electrical is Division 40 through 49. Okay, and you can see all the different divisions within electrical itself. Just giving you a chance to look at it yourself, because you never know. I mean, you look at Division 48, electrical power generation. It's like, wow, I've always wanted to know what that was, and okay, so now you know. There's no, this is the breakdown. Division 22 is plumbing, you know, but within plumbing, it's a sub breakdown of a subgroup. So I didn't put all of them in here. I picked one. I said, well, let's pick on plumbers, you know, so let's grab their Division 22. So here's the breakdown, the subgroups. You know, you have plumbing is 22, but 2210 is your plumbing and piping, then unassigned, then plumbing equipment, plumbing fixtures, pull and foundation plumbing systems, gas and vacuum systems, and so on. So it breaks it down even farther for us. Okay, so we can put them in these subgroups. All right. So there's the breakdown a little bit. And again, it's okay, section numbering, section 5, that would be the division number. Like 5 is metals, you know. Then you have 053. Now, 5 is metals, 3 is a broad scope, you know, which covers under it metal decking. Okay. Then you have 531, and that's the medium scope steel deck. Okay. Break it down even farther, you know. metal, broad scope, medium scope, narrow scope, roof deck. So it's just breaking them all down for you, which I'm sure y'all know that, and like, thank goodness. Direct conflicts or ambiguities within the documents. Now, contracts usually provide that the design professional decides. Otherwise, provisions on the plan but not in specifications, or in specifications but not on the plans, must proceed as if it's in both. Ambiguity between the plan provisions and printed specifications must assume specifications control. Okay, the written overrides the drawn, in other words. If it's in the specifications and not on the plans, then use the specifications. Conflicts, direct conflicts or ambiguities within the documents. Now, the contract usually provides that the design professional decides. Otherwise, provisions on the plans but not specified, or in specifications but not on the plans, must proceed as if it's on both. Now, the ambiguities between the plan provisions and the printed specifications must assume specifications control. So the written overrides the drawn is what it is. Okay? Specifications take control. Now here, methods of drawing, sketches, and plans. All right, now we all have to use these. Purpose of drawing: show locations, arrangements, and dimensions of components. We show elevations, which are head-on, okay, usually vertical views. Now it shows detail sheets, which are important for accurate estimating, and more important when we're building, so we know how to put it together. I mean, somehow, somewhere, the rumor got out that building was easy. It's like, oh, anyone can do it. It's like, really? It's easy? Yeah, oh yeah, we have all these people get a license to build these homes and buildings, and it's like, well, have you ever done it? No. Maybe you should do it before you don't want to get a license to actually do it yourself, and take all the responsibility. If anything happens, they hold us responsible, but see it done all the time. It's, you jump in, you try to do something, which is okay, all of us, we didn't know it all, but we surrounded ourselves with smarter people. And hey, how do I do this? Hey, how do I do that? What's going on here with this? We start out slow. It doesn't do anyone good to put them in a position of a superintendent without them ever being out in the field. Now we have ortho, okay, perspective. Now, concepts of orthographic perspective. Ortho means perpendicular or right angles. Now, orthographic projection has been found to be the clearest method of showing true shapes, relationships of features, and necessary dimensions. Okay, and there's our floor plan. Okay, our residential floor plan. Now notice we can see dimensions, wall lengths, okay, the layout of the entire house. Just giving you a second to look at it. I'm sure you look at these all the time, okay, but for those of you who do not, now notice here, you always see typically, not always, geez, you see an overall dimension there, like 63 feet. Then he goes down and breaks them all down. Well, this is the wall, here's a window, here's another window, so it shows us the windows, doors, steps. Over to the right here, it shows us our concrete steps. Okay. So we can see here's a sun deck, on the back of the house. So as we come out of our master bedroom through our French doors, we can come out here on this sun deck and, relax and, okay, chill. Now notice you can only get to it from the master bedroom. So we don't want other people bothering us when we're out there. So that's understandable. So we have our layout of our home. Now this is an elevation or section view. Now notice, this deck right here. Notice under 4.3, it's detailed drawing 4 found on page 3. So in my plan set, I know exactly where to go to see. When I see this is showing me that this line right here, let me get my pointer, is if I cut through this deck entirely and I look to the north, this is what I would see right there. So at a cut view, at a whole section. Now this is just a break line saying it's the same, so instead of drawing it all the way, it's 12 foot 8 inches. It's the same all the way. Okay. So now I can see, okay, here's my footing, here's my rebar, here's how deep any excavation I need to be going. Here's some details up here about my deck. What are my posts and balusters and railings and joists and decking planks and so on. So everything is there for me. So if I'm in the plan set looking at the foundation plan and I see this and I want more of a detail for the deck, then I know to go to page 3 and I would see the detail for 3. So that's why we always look for them on the plan set. Now, ISO perspective, concepts of isometric drawings. Now, isometric drawings are pictorial in nature, yet they are compatible with orthographic drawings in that 3 sides are shown in an isometric. Now, most of us have seen isometrics, and a lot of us have used isometrics. We see them on our plan set. Now, here's a plumbing isometric. It's drew out for us, and it's, in an isometric detail view, so we can see, where the pipes are going, where our vents are going, where our bathroom fixtures are, where our lavs are at, our showers. Okay, we have a whole bank of them right there. So that's what this is showing us. So we can see when we do our plumbing, the layout of everything and where everything goes. Okay. Then we have architectural scale. Now, architectural scale is calibrated into feet and inches and conventionally reduced scale, so the large buildings and details can be conventionally drawn on manageable size of paper. So everything is scaled down. So here's a scale. This is an example of an 1/8 inch and a 1/4 inch scale. Okay. Now, you got to remember when we're doing this, here's 0, 1, 2, 3, 4, and so on. Now, in quarters, we read it the opposite direction. So one way in 8ths, you read it this way. In quarters, you read it in reverse. See how the numbers are closer? And it looks a lot harder than what it is. Once you do it once or twice, you'll get real good at it. It's just having a scale laid out in front of you, playing with it, but again, once you get used to scaling things, it is a lot easier. Now, there's 11 scales in architectural, and I listed them all out for you. You can go a 1/16 of an inch, you can go 3/16 of an inch, and what that is 3/16 of an inch is equal to 1 foot in actual length. or you have a 16th of an inch is equal to 1 foot. So that's how they drew it on the plans, okay, so that we could scale it. All right, now engineering scales are a little different. Actually, they're a lot easier. Engineer scale has 6 different scales. They're as follows. 1 inch is equal to 10 foot. 1 inch is to 20 foot, all the way up to 1 inch is equal to 60 foot. So, for me at least, I think the engineering scales, is a lot easier to use than the architectural scale. But, both of them's doing the same thing. So it really doesn't matter. No scale in metric, okay? All drawings are non-dimensional ratios, okay? In other words, 3 inches equal to 1 foot standard. Engineering, there is no 3 inches to 1 foot. In metric, it's 1 to 5, or 1 to 10, or 1 to 20, or 1 to 50. So metric is a little bit different than, your standard or your engineering scales. But most of us don't use metrics, so okay, it's a moot point. Now, drawing and designing using metrics, use only millimeters on a drawing, except for larger, cartographic drawings. Delete all unit symbols. Whole numbers always indicate millimeters. Decimal numbers taken into 3 places indicate meters. Design should hold to the metric 100 millimeter module. Now, this is just showing you, your different orientations. And, once again, I think a lot of people already know this, that, whenever you take something in portrait, the page is laid out like this, like a standard sheet of paper. Landscape is when you turn the paper sideways. Okay, so it's like this. Even in photography, you can either take it out of portrait as a landscape. And I'm one of the people that are anti-portrait. It's like, guys, if you're going to take a photo, turn your phone sideways, But I've been doing photography for so long, it's like you never take, portraits, But I guess with the cell phone and the new technologies, a lot of people are doing it now, so maybe that's the new way to do it. So everything's changing. But we're talking about drawing in our plan sets, so same concept. Now, here's our standard sheets of paper. Now, as you can tell, it gets confusing, because size A for an engineer is 11 by 8.5, but architecture it's 12 by 9. It's like, are you kidding me? But yet, when you see most of the stationery anymore, it's A1, A0, A2. So it's changing. Now, is it going to change anywhere soon? No, but it is. A lot of it is changing. Unfortunately, we're dealing with English and metric, and we're going to keep dealing with it. So the rest of the world is using metric, and we're using, the English system or architectural, and it's half and half. So we're mixing units is what we're doing. How the metric system is structured, and it's trying to show you here. Everything's in units of 10. There's a cubic meter right there. So we have millimeters. 10 millimeters is a decameter, or a centimeter. I'm sorry, 10 centimeters is a decameter. But everything's in units of 10. So a cubic decameter is a liter. So now notice, it's hard to understand until you actually start using it. And then once you start understanding it, wait a minute, this is units of 10. We can do this. and we can. You know, the initial concept, the hardest part about the metric system is someone sitting down and taking a few minutes and looking at it. You know, once we look at it, you know, we start to understand, wow, might actually help me, you know, and be easier for me. But nah. So we have length, you know, meters is a symbol of M. Mass, we use grams, symbol of G. And capacity, we use liters, okay? And that's symbol of L. Now, personally, this is just me personally, I was moved to Germany, Europe for, you know, a few years. And it was easy to go from the English system to the metric system. It was harder for me, believe it or not, to go from the metric system back to the English system. You know, because once you get in the thought process of liters and grams and meters, and it's harder to switch back than it was for me to go to the metric system. So here's how we have deca, okay, 10, okay, 10 centimeters. Hecto is 100. Kilo, 1,000. Mega, okay, 1,000,000. And giga, a billion. Okay. So units without a prefix of 1, you have, which is less than a meter. Decimeter is 1/10. A centimeter is 1/100th. A millimeter is 1/1000th. And then we can actually go into micro, which is 1,000,000th. That's when you're really getting tight in the answer range. And the symbol of mu, Greek alphabet, backwards U. And nano, okay, 1/1000th. Okay, so a nanosecond is 1/1000th of a second. Okay. Now, this has been many years since, you know, someone's actually made you sit down and do this and think about this. Okay. Now, for construction drawings, we have kilo, K is 1,000. Okay. Units without the prefix of 1 is milli. You know, that's your millimeters. Okay. 1,000ths. So you have kilo, okay, 1,000, and a milli is 1,000ths. Okay. Base units change only allowed in magnitudes of 1,000. Okay, which is helpful. Now the meter is roughly 39 inches or 3 foot 3 inches, 3.25 feet, or 3.28 feet is a meter. So it's a little more than 3 foot 3, but it's a rough estimate. The millimeter is about 1/25th of an inch. Okay, it's 1 millimeter. Okay, they're roughly 25 millimeters per inch. And this is how we estimate it real quick in the field. You know, an inch is about 25 millimeters. You know, 100 millimeters per 4 inch. 300 millimeters per foot. Okay. 1,000 millimeters per yard. Okay. 1,000 millimeters squared is a square yard. Okay, a 2 foot spacing would be about 600 millimeters. A 4 foot sheet of plywood is 1,200 millimeters wide. 1,000 millimeters cubed, remember that's 3 sides, is about 35 cubic feet or 1.3 cubic yards. Now, I think, you know, our generation, I mean, I'm talking about 40 or and older, you know, we're not going to switch to the metric system. Now, the younger the group gets, the more we're going to see metric system. Okay, we're already seeing it. You know, look at some of your, you know, your plumbing fixtures and pipes and electrical, and you know, they're already in meters. You know, so we're getting there. It's just a little bit at a time, and we're mixing units as we do it, which is dangerous, but maybe our grandkids, will be switched to metric system by then. Okay. So a pound is 0.453 kilograms. So calculate the mass of a 100-pound person in kilograms. So 100 pounds is 0.453. That's 45 kilograms. All right, so that's pretty easy to calculate. And anyway, whenever I go to the doctor, I always set the scale for metric. So I seem, well, how much do you weigh? I weigh 120 kilograms. Makes it sound better. A gallon is 3.785 liters. So it's not quite 4 liters, but it's close, 3.785. Calculate the liters in 5-gallon buckets of water. Okay, well, 5 at 3.785 is about 19, liters of water in a 5-gallon bucket. Okay, then it says calculate the mass of a 5-gallon bucket of water. Okay, so take 5 times 8.33 or 8.34, however you want to use it. I'm not going to argue about, a hundredth, spot. So 5 times 8.33 is 41.65 pounds. Now all we have to do is multiply that by the 0.453, and that's 19 kilograms. All right. So there's 19 liters, and it weighs 19 kilograms. Okay. In cubic, there's 7.5 gallons per cubic foot, or 7.48. People want to get sticky. Oh, well, wait a minute, Rich, you're, 2/100ths of a pound off, So a millimeter, just, when you're out in the field, just how we do it. I can look and say a millimeter is about the width of a paper clip. This. 10 millimeters is about the width of your fingernail. Okay, your small finger, average. 100 millimeter is the width of the hand. Okay, and that's going from your thumb all the way across. And 1,000 millimeter is typically from one shoulder to the tip of your fingers. Now, that's 39 inches, but a lot of us, we're different sizes. Okay. But again, that was just an average of the way they do it, is all it is. So it says to convert circular mills to cubic millimeters, that's 5.067. Okay, 075. So interpreted as, 5.067, 075 times 10 to the 4th power, which yields, 0.000. Yeah, 5067075. Now you can convert kilowatt to joules, or joule, it depends upon what day of the week it is. Okay, so interpreted as 3.6 times 10 to the 6th power, which yields 3,600,000 kilowatts an hour. So the title sheet of the drawing sequence is the first sheet contained in the plan set, and it contains the name and location of the building project, name of the architect or engineering firm, an index of the drawing, and usually the legend or key for materials used in the drawing sheets to follow. So that's the first sheet for you. Now, the civil series, C1, C2, C3, and so on, contains the location, the plot plan, the boundaries and setbacks. If soil borings were performed, the bearing capacity of the soil at each boring location will be shown, and all property accessories such as walks, drives, outbuildings, utility locations, etc. Okay, that's our civil series of prints. Okay, C1, C2. Architectural series, horizontal cut or bird's eye view of the building's floors. Okay, so we can see what we're building. The vertical cut, okay, person's eye view of the building and wall sections. And we have elevations, north, south, east, and west. Okay, so we can see all sides of the home or building and what they would look like standing from the ground looking. Now, trade discipline series, of course, structural is S1, S2, and they make sense. They did try to keep these, mechanical, HVAC, M1, M2, plumbing is P1, P2, electrical is E1, E2, swimming pool, SP, so they did try to use these and make sense of them, okay, when they label them for a change. I mean, someone's going to come and change it, I'm sure, because it does make halfway sense and it's not normal. Okay, let's look at some of the math here. Okay, so we can look at the plans. Now, I put this in here so, people can actually understand, and I'm sure you do, how to read an inch. An inch is just simply broken down into sixteenths. And I wrote them all out, 1/16, 2/16, 3/16, all the way to 16/16, which is 1 inch. Now, my biggest issue with this is people make fun of people out on a job site because they can't read a tape. I've seen it over and over, and I'm sure you have too. And it's like, guys, do you realize that they're working for you? The joke's on you. If they can't read a tape, that means they're going to make a mistake. And they're your employee. You need to be teaching them how to read a tape. So as an employer, we have a certain responsibility to train our employees, how to use our tools properly. Who else is going to teach them? YouTube? Well, it is a good source, but no, it's up to us to train our employees. Now, this is just a foot broken down into 12 inches, to impress you. So now wow, 1 foot is 12 inches. It sure is. Now, the reason I did this is I always go back to the whole units. In math, especially when you use an English system, we have to convert numbers back and forth. So if I'm in feet and I need to go to inches, well, a foot has 12-inch increments in it. So if you take a foot and multiply by 12, it's going to convert it to inches. So everyone would understand if I said, listen, I need a board 1 foot long. Okay. If I said, listen, I need a board 12 inches long. Well, the same group would understand me and know what I wanted. So no worries. It's when we get into the fractions, like a half inch. Hey, do we got any boards that are 0.0416 feet thick? What? Yeah, I need a board 0.0416 feet. Most people, none of our employees are going to know what that is. We have to convert it for them. If you take a half inch, 1 divided by 2 is 0.5, half. And then take half and divide it by 12, okay, is 0.0416. Remember, if you have 12 whole inches and you want to know how many feet that is, mathematically divide it by 12, and that'll tell you that it's 1 foot. So it's always inches divided by 12 converts to feet. Feet times 12 always converts to inches. So it's always going to work back and forth. Now, the fractions, you have to convert the fractions before we convert anything else. So convert the fraction into inches and then divide it by 12. So what we're doing as we're doing this. We do have a basic math, but I covered that in another module, so I don't want to go through and cover everything again. So I'm assuming everyone's already read it and understand it. Okay, so now we can go ahead and go forward. So we're always going to take our inches and divide it by 12. Now fractions, go back to the, 5th grade. where my teacher was standing up in front of the room going, the numerator divided by its denominator. She smoked. I'm sorry. Will give you a decimal equivalent. So 3/4, 3 divided by 4 is 0.75. Okay, rock on. 3 divided by 8, 0.375. So it's the same measurement. I'm not changing the measurement of anything. I'm just saying one is in a fraction, the other one's in a decimal. But it's the same measurement. A 16th. We take 1 and we divide that by 16. Is 0.0625 inches. Okay? So it's the numerator divided by its denominator, the top number divided by the bottom number. Okay? Yeah, a lot of times in math, especially in estimating, the more you do something, the more you guesstimate things. We don't accurately estimate all the time doing estimating. We guesstimate. We'll look at a circular shape and square it up. Reason being is I know I don't want to run short on concrete when I order it, so I always want to order more than I need, so I end up rounding up. Here's a 20-foot, diameter circular patio slab. Okay, well, that's I'm just 20 by 20, and how thick is it? And go on, Now, there's some of us going to go, well, that's pi r squared, it's pi times radius times the thickness of the slab, and, that'll give me an exact quantity, which, okay, but what's the minimum loads you can order? So there's a lot of variables that go along with that, but testing is exact. That's trade knowledge. You have to know that, okay, my truck's I can only order, what in a truck, how much concrete in a truck. So how many trucks do I need to order? Okay. And they'll never short you at all. Concrete trucks don't do that. Okay. I mean, there's no way I could see that guy coming down the road and go out there and give him, $100 to pour me a little slab out of your load, and now you're short, but he made $100. So fortunately, it happens every now and then. Okay, so what we're going to do now is look at some of the constants that we use in construction. Here's some of the square constants, area. 144 square inches a square foot, 9 square feet in a square yard, a 3 by 3. And roofing, 100 square feet in a square. And when we look at our lots, our property, 43,560 square feet equals 1 acre. Just a constant. Now 1728 cubic inches in a cubic foot. Remember, this is 12 by 12. That's square. That's an area calculation. This is cubic or volume. This is 12 times 12 times 12, which is 1728. So these are three-dimensional down here. These are two-dimensional. So a cubic yard, remember, it's 3 foot by 3 foot by 3 foot. 3 times 3 times 3 is 27. A cubic foot will hold 7.48 gallons of water. Wow, at a constant, it never changes. Let me go on and show you the next page of what they are. A gallon of water weighs 8.34 pounds. They took a gallon and set it on a scale. There's what it weighed. A cubic foot of water weighs 62.5 pounds, or 62.4 either way. I rounded up because 62.5 is a lot easier to remember than 62.4, and it doesn't matter. Close enough for us. It's 231 cubic inches of water in a gallon. That's true. Now I'm trying to think where I would use that, but the only time I know that we use it typically is when we're calculating our paint. When we go into our paint, we can use 231 cubic inches in a gallon. But other than that, we don't use that too much. 2,000 pounds is a ton. That's trade knowledge. They didn't put that in our estimating books. They just said, well, everyone knows that. And believe it or not, I've had students in class who don't know. It's like, wow. I learned that when I was 10. My dad, hey, you're going to shovel some rocks, boy. It's like, damn, Hate rocks still to this day. 1 meter is 3.28 feet, 3 foot, 3 inches. You already went over that. And a mile is 5,280 feet. So if you walk 5,280 feet, you walked a mile. Okay, 1 mile in length. Now here's where we would need, okay, to use in our plans. Okay, it says to verify the building's layout for square before excavating for wall footings, a contractor sets up batter boards 3'6" outside the four corners of the building. Now the strings intersect on the outer face of the 8-inch by 8-inch by 16-inch concrete masonry unit. What is the diagonal distance from the string intersections at the northeast and southwest corner? All right, I'm standing out on the lot first thing in the morning, and I'm trying to verify what I'm building is laid in square at 90-degree angles. Now, it depends upon where you work. Over here in the Hudson, on the west coast of Florida over here between Elfers and Arapika, we're just 40 miles north of Tampa. We're on the poor coast. We don't worry about stuff like this. I mean, that's pointless to us. But everywhere else, we need to figure this out. We want to square our buildings. So when our framers come in to put the walls up, they're okay. And roofers go the guys go put the trusses on, they said okay. And, but it's boring, no challenge in the jobs. So I looked at the plan set, and I showed you this a while ago where it was, 63, at the top of it, and it was 53 on the side on the foundation plan. And I said, okay, what I'm going to do is I'm going to set up some batter boards, 3'6" outside the four corners of the building. Now, that's just where I chose to put them up. I mean, if it was a, holiday and I'd been drinking the night before, I may put them 6'6" outside the four corners. I don't care. It's where the strings intersect is what I'm caring about. I'm going to have those strings intersect on the outer face of the footings. Or no, outer face of the wall. Jeez, I told you. I was drinking last night, I guess. But anyway, no, it wasn't. Put them up on the outside corners of the building. So I'm going to check from corner to corner on the outside face of the wall. So that distance. Now, look. Everyone knows this. North, top of the bottom of the page is south, and then we spell we, W-E. So this would be the northeast corner, of course, and down here would be the southwest corner. So that's what I want to do. I want to measure that. Now, if on the plans it says this is 53 feet, and this dimension is 53, 63 and 53. Now, I'm going to use a right triangle leg length. I went over that in a previous module. A squared, B squared, C squared. Okay. So I'm going to take the square root of 63 squared plus 53 squared. Now, it doesn't matter which one you label A, which one you label B. The hypotenuse, or the long side of the triangle, is labeled side C. So I'm going to say the square root of A squared plus B squared. So 63 squared plus 53 squared. Now, 63 times 63 is 3,969. 53 squared is 53 times 53. That's 2,809. Now, add the two together, 3,969 and 2,809. That's 6,778. Now, what number times itself is 6,778. And when I hit my square root key on my calculator, it unsquares the number and tells me one side of the square. And it says that's 82.33 feet. 82 foot 4 inches. Remember yesterday when we went over our math, we said, well, or in the previous module, 82.33 is 0.33 is 4 inches. 4 inches divided by 12 is 0.33 feet. Now, that's 82 foot 4 inches. So if I took the same tape that I have measured here, and I don't move anything. I hold my hand on 82 foot 4 inches. I'm going to turn it around and measure from here to here. Well, from there to there. You get what I mean? And it has to measure 82 foot 4 inches. If it measures anything other than 82 foot 4 inches, you're not laid in square. You're off somewhere. You're not at a 90-degree angle here. So you got to go back and adjust till you are. Okay, which you know that. All right, here's just a little visual of what we're getting ready to do. Now, this is a foundation plan. I think it's on A06 of the plan set if you want to look at it. Now, notice the little circle that's drawn around a pile cap. Now, do my pointer. The box around there, the square, is a pile cap. The dots are the piling. These lines here are the grade beams that are connecting the pilings together. But what is it? Okay, so what that is there's 4 wood pilings, okay, driven in the ground. Now, around the top of the 4 pilings, we embed these pilings up into the pile cap like 3 inches or so. Okay, now we bring in reinforcement steel to strengthen them. Now, some of them are so big they have 2 mats in them. That's 1 mat of rebar. And then we place the concrete in them and embed the pilings up in there. And then in the concrete, we embed some anchor bolts. Okay, that's a grid point, B2, B3, C2, C3. It's where the lines intersect on our plan sets. Okay. Now here comes a base plate. Now it usually has grout bed under that. And then we put the base plate on. Now we connect the column to the base plate. Now it shows me that's a W8 by 60. Now that tells me it's a wide flange steel beam. It also it's 18 inches in depth, web depth, and it weighs 60 pounds per linear foot. So it tells me the shape of the beam, the depth of the beam, and the pounds per linear foot of the beam or column. Okay. And then, of course, our grade beams, our pile caps are connected together with the grade beams, and our grade beams have reinforcement steel in them. That's the little round dots that you see. So that's what that picture is trying to explain to us right there. Okay. There's an empty lot with a bunch of pilings driven into the ground. You know, and if think about marine, what are they at? $1,200 a piling now? There's our boats. There's our guys out there with the base plates and the boats on it, and they have their hard hats on. Okay, good guys. This is a column and pile cap schedule, A11 in your plan set. Now look at what this tells me. Here's grid pile caps marked number 2, and they're at grid points B2, B3, C2, and C3. There's 4 of them there. Now this is the column. It's a W8 by 60. Wide flange steel beam, 8 inches in depth, and it weighs 60 pounds per linear foot. So right there tells me the weight of it, and I know I got 4 of them. I know the length. What is it from here to here? Well, from first floor line up to the top of the column is 25.50 feet. And from the finished floor line to the top of the pile cap, so I'm at the bottom of the column, that's a negative 3.5 feet down. So if you add 3.5 feet to 25.5 feet, that's 29 feet. Okay. I got 4 of them. They're 29 foot each, and they weigh 60 pounds per foot. Here's my information about my base plates. I'm using a 2-inch grout bed. My base plate is a 16-inch by 16-inch by 1.5-inch thick. I got 4 pilings below it. The depth of the pile cap is 2 foot 4 inches. I'm going to place number 5 rebar at 6 inches on center each way. So I'm going to have top and bottom 2 mats of rebar, one at the top of it, one at the bottom of it. And there's a plan view. They're 5 foot by 5 foot pile caps. I'm using 1-inch diameter bolts. I have 4 of them. Okay, for the base plates. So it tells me quite a bit right here is what I'm trying to get at. Okay, quite a bit of information on the plan. So it says refer to sheet A06 and A11 on the plan set. The total weight of W8 by 60 steel columns placed on pile caps at grid point B2, B3, C2, and C3 is how many tons? Well, again, we did this. How many steel columns do I have? I have 4. Now, how long is each of them? 29 foot each. What does it weigh? 60 pounds per foot. And the one bit of trade knowledge, how many pounds are in a ton? It is 2,000. So if you didn't know that, now you do. So I have 4 columns that are 29 foot each. That's 116 feet of columns. It weighs 60 pounds per foot. I have 116 feet. So multiply the 116 times 60. Now you know it's 6,960 pounds. Now all that's left to do is divide it by 2,000 because 2,000 pounds is in a ton. Then you have your answer. 3.48, answer C. Okay, 3.48 tons. Now if you'd have made a mistake and you would have put and only calculated 1 column, there's the answer. If you'd have missed the 3.5 foot section below first floor, there's the answer. And if you'd have calculated all the columns in the building, there's the answer. So it's easy to make a mistake whenever you're testing. This is right out of the code book. It tells us our crickets. Chimneys shall be provided with crickets with dimensions parallel to the ridgeline is greater than 30 inches. So if it's 30 inches or less, none's required. And that's in our residential code 100.320. Now to me, I don't care what size it is, I'm going to put a cricket up there. You know, a cricket, let me show you on the next page here. A cricket simply is going to divert the water around that horizontal surface right there, the chimney. So it doesn't constantly hit that and eventually causing it to leak. So this way, as the water comes down, it just sheds off and runs off the roof. Okay, or a saddle. There's another one. So all it does is divert water, you know, as it coming down and it runs it, okay, off the roof. So the code says chimney shall extend not less than 2 feet above, 2 feet higher than any portion of the building within 10 feet, but shall be not less than 3 feet above the highest point where the chimney passes through the roof. Okay, direct code, right out of the code. Three feet up, or 2 foot higher than any portion of the building located within 10 feet. Okay, so wherever we come within 10 feet, we got to go 2 foot higher. There's cricket on one of our events. Now, some of you look at that and you think, wow, that's just like a shingles popped up and turned up. Well, see, that's where you're wrong. You're just not experienced enough to notice that as a cricket, so divert water around that pipe. So the pipe doesn't leak. I mean, come on, what a sharp roofer. This just going over telling us not be careful when we're notching and drilling our joist and studs. Now, keep in mind our joist. We always leave the center third section alone. It's something I've learned, day one in construction. Hey, if you have to notch or drill the ends is okay, but leave the center alone. Okay. So I can notch up to 1/6 of the top or bottom of the joist. Okay. 1/6, notch it out. I can drill up to 1/3, but I have to remain 2 inches from either edge there. So sure, I can drill up to 1/3 of the board as long as I remain 2 inches from either side of it. Okay. And the center third section, no one touches it. Well, I say that, but somewhere, and I haven't found it yet, I've been looking for it for years, somewhere in the mechanical code and the plumbing code, there has to be an exception where it says, except if you're a plumber or an AC contractor, then you do whatever the hell you want to do. If you need to bore it or notch it, if you need to cut 3/4 of it out, go ahead. They missed that part of the code, or I missed it. So, but I'm sure it's in there somewhere. I just got to find it. There's one AC cut. Now this is a triple joist, and someone notched half of it out. And to me, it looks like that's the AC contractor. And again, well, just don't care. He got his job done. It's as bad as us telling a plumber, hey, put a 4-inch pipe in a 3.5-inch wall. They'll do it. It's a little bold, but acceptable methods. There's our studs there. And yeah, whether it's a bearing or a non-bearing stud, it does make a difference. I mean, for the hose, we can drill up to 60% of a non-bearing, but only 40% of a bearing stud. And either one, we have to remain 5/8 of an inch from either edge. Okay, so 5/8 of an inch from the edge, 40% on a load bearing, 60% on non-load bearing. And when you're notching it, go ahead and notch up to 40% of that non-bearing stud. But if it's a bearing stud, you can only notch up to 25% of the stud out. Okay, so those are things we need to remember, as we're framing and building our buildings. Now, this is just a quick mathematical calculation to scale. A wall measures 4 3/8 on the plan. If the plan scale is 1/16 of an inch is equal to 1 foot, what's the actual dimension of the wall? Well, this is where a lot of people jam. Now, to me, I always just tell them, listen, put everything in, a proportional format. I know that 1/16 of an inch, remember 1 divided by 16 is 0.0625. 1/16 of an inch is equal to 1 foot in actual length. The reason I converted it is I can't plug a fraction into a standard calculator. My calculator, I cannot plug in 1 divided by, or 1/16. Now 1 divided by 16, I can plug in 0.0625 and that's fine. So that's why I have to convert the numbers. I can't plug in fractions. So 1/16 of an inch is equal to 1 foot. Then 4 3/8, 3 divided by 8 is 0.375. Is what an actual length? Well, I know the plan scale is beneath the plan scale. The number of feet are beneath the number of feet. I have two corresponding facts side by side, and I'm looking for that fourth and unknown fact. Once I have it set up like this, simply diagonally multiply this and then divide by whatever's left. So I'm going to multiply by 1 and then divide it by the 0.0625, and that's going to tell me an actual length. That wall is going to be 70 feet long. All right, giving everyone a second to think about that one, just to make sure they understand the math. So the easiest way is always put them in a proportion. It'll walk you right through it.